Hello everyone, I'm Dr. Jyoti Mandala. Welcome you all to the video lecture series on the course Operating System. We are learning about process synchronization. In our last lecture, we have learned in detail about what actually this critical section problem is. I'll quickly revise that one. Critical section is nothing but if more than one process is using a shared resources like your global variables or of some files which are common between multiple process, then those shared resources or shared variables need to be put in this critical section so that there should not be any race condition. Now, to give the solution to this critical section problem, we have two approaches. We already learned in our last lecture, like we have highlighted them, like software solution and hardware solution. This Peterson solution is your software solution. Also, in our last lecture, we learned about any solution to the critical section problem must satisfy three requirements: mutual exclusion, progress, and bounded weighting. We have understood in detail what are these three requirements are. And also, we understood a simple structure of your critical section, which consists of entry section and then critical section, after that exit section. Today, we will be understanding in detail how this Peterson solution will give a solution to your critical section problem. As we already know, this critical section problem is a software solution. So make a note all of you, this is a software solution. All right. Now, what actually this Peterson solution is? This Peterson solution will help us in giving a solution uh, for accessing the critical section, where in this section we have our shared resources available. Okay, now this critical section will have a constraint here. The constraint is this critical section problem will work only for two processes. That means if you have only two processes, then you can adopt this critical section, Peterson solution. Peterson solution will give solution only when there are only two processes competing to enter into the critical section. That means, suppose if you have two processes like P0 and P1, then this solution can be applied between these two processes. If you have more than one process like P0, P1, P2, P3, P4 like that, this Peterson solution cannot be used. I hope you all are understood. So this is a main thing you need to remember, all of you. This Peterson solution can be applied only between two processes. Okay. Now how this will work? Now if two processes are there, then if P0 is in the critical section, then P1 should wait. And if P1 is in critical section, P0 should wait. So how to achieve that one? To achieve that one, it is using two data structures. Make a note all of you. It uses two data structures. Or else I will just type that. It uses two data structures. The first data structure is first one is a variable called turn variable. What is this variable is? This variable indicates whose turn it is now to enter into the critical section. This indicates whose turn to enter into the critical section.
So critical section, let me represent it with CS. Generally, its value will be, the turn value will be, it can be either 0 or 1. That means if critical section, if the turn value is 0, that means process P naught, it is the turn of P naught to enter into the critical section. If the turn value is 1, then it is now the turn to enter P1 into the critical section. Okay, now next data structure we will be using in giving the solution using Peterson solution is variable called flag. Here, as for the turn, as it is 0 and 1, we will use the data type int. Int data type can be used. The values can be either 0 or 1. Coming to the second data structure, that data structure is an array of type boolean. Now this uh, data structure which is flag of array size of 2. So the use of this data structure is, it will help in knowing the interest of a process to enter into the critical section. So its value can be either true value or a false value. Right? Its value can be true or false. Now, what is this true? What is this variable will tell is, suppose as it is a variable array of flag 2, you will be having flag 0 and flag 1. Now, flag 0 can be true or false, flag 1 can be true or false. Suppose, as an example, I will take, if flag 0 is true, it means process P naught is interested to go into the critical section. Turn defines next whose turn it is. Flag defines the interest of a process to enter into the critical section. Okay, flag 0 is true means P naught want to enter into critical section. Right? I hope you all are clear. Alright. Now, initial values of flag 0 and flag 1 is 1 only. Initial, sorry, not 1, it is a Boolean data type. So, initial values are false. That means both of them are not interested to enter the critical section. We will assume like that. All right. Now, how it will work? So, these two data structures will be used. Turn variable, which is of int data type, and flag of 2 of array of Boolean data type. So, we will be having only two processes, that is consider P0 and P1. Okay. Now, the general code for this Peterson solution is given like this. We will see that one. So this is the general code for a process PI. If you consider process PI, and another process PJ wants to enter into the critical section. For a process PI, the particular code snippet is given like this. You can understand from here. While flag of I equal to true, that means always whichever process you are taking, that process has to tell its interest to enter into the critical section. That's what we have understood using flag of an array we have taken. So flag of I equal to true, it means process Pi wants to enter into the critical section. Then it will turn after me, my next turn it should be J. So it will make turn equal to J, whose turn it is. Okay, now coming back to here, while flag of j equal to true and turn equal to j, then if you know the operation, logical operation, ent operation, if both are true,
then only it will be true. If one of them is false, it is false. Right. Now flag of j is true. Initially flag of j will be false only, isn't it or not? Why? Because the initial value you can see here, the initial value is false only. So flag of j is false only. Right. And turn equal to j. Yeah, turn has been made to j, but flag of j is false. So this becomes false and this becomes true. False to equal to false. Totally it is false. So once the condition becomes false, it will come out of this one. Why? Because we have semicolon here, and then now process pi can enter into the critical section. Now this section, whatever we have mentioned here, is called as entry section. This is called as entry section. Okay, now once we have got an option of here false and true. Why? Because as it is false, pi is in critical section. Now once pi has completed its critical section, it will come out of that one and it will tell flag of I. That means now I don't want to enter into the critical section. Why? Because it is giving an option to the other process to enter into the critical section. So this part is called as exit section. Okay, so this part is called as exit section. Now, in the last class, we have learned in detail the structure to be followed by a critical section problem. A critical section solution should have the entry section, and then a critical section, and then the exit section. Did you see here the Peterson solution is following that one? Okay. Now this is general structure for a process PI and PJ. Let us adopt that one, apply that one for P naught and P1, and we will see whether it is working properly or not. And also those three requirements of mutual exclusion, progress, and bounded weight are satisfied or not. Okay. So let me write first the code for process P naught. Okay. Just replacing in this code, wherever I is there, it is P naught. Wherever J is there, that is P1. Okay. Similarly, let us represent process P1 also, how the code will be further. And then we will see whether it is following those three requirements or not. Okay. What we have done here, we have followed this general structure. What is this general structure? This general structure, wherever I is there, for that P naught should be 0 and for P1 it will be 1. Okay, right. Now let us understand these two and how it is working. We will see. Okay, now let us initially for P naught and P1, that means what is that? Flag of 0 is false and flag of 1 is also false. Okay. All right. Now, let us consider we have P naught wants to enter into the critical section. Whenever a process wants to enter into the critical section, it will start its execution. You see here,
P naught wants to enter into the critical section. So now what it does? It will execute this statement. What is that statement? P naught flag of 0 will be true now. That means now this has been changed to come here. It is telling turn equal to 1. Okay, turn equal to 1. Initially, now earlier the turn is for now we can say 0. That means this is the turn of process P naught. But as the process P naught executed this one, turn equal to 1. So this has been changed to 1 now. Now commensurate flag of I equal to true. Flag of 1, sorry. Flag of 1 equal to true. What is flag of 1 which is false? So this is false. Next, turn equal to 1. Yes, turn equal to 1 which is true. False and true is equal to what? Totally it is false. And operation, it will return to false. As the flag while operation is false, it will come here and it will go into the critical section. That means P naught is in the critical section. While P naught is in the critical section, we need to check if process P1 wants to enter into the critical section, whether it has been locked or not. Because in our last lecture, we told this option of entry is called as locking, and this process of exiting is called as unlocking. Now, once P naught has entered into the critical section, it has to lock this one, isn't it or not? It has to lock this one. Locking is nothing but if P1 wants to enter into the critical section, it should not be able to enter into there. Let us see that one. Flag of 1 equal to true. That means this has been changed to true. Now it is telling the turn equal to 0. So this has been changed to 0. Okay. Now flag of 0 is equal to true. Flag of 0, yes, it is equal to true. And turn equal to 0. Turn equal to 0, which is also true. So true and true is equal to true. So what happens? It cannot come out of this one as it is in the condition is true. When it can come out of this one? Whenever the condition becomes false. That means it will be in this condition. Keep on checking this condition until the condition becomes false. Okay. So now P1 is in this loop only. It can't enter into the critical section. I hope you all are clear. That means we have achieved our first requirement. What is our first requirement? Mutual exclusion. Mutual exclusion. What is that mutual exclusion says? In our last video, we have understood. If one process is in the critical section, in our case, P naught is in the critical section, another process should not be entered into the critical section, which has been done by the locking process. Got it? Now, second, let us see the other two also. But meanwhile, let us see if P1 comes out of the critical section, whether if P naught comes out of the critical section, if P1 can enter into the critical section or not, we will see. Okay. Now, P naught has done its work here. Now, P naught has come here and it is executing. P naught has completed its part and it has come here. What is its task? It has to set flag of 0 to false. Now flag of 0 is now set to false. Now the moment flag of 0 is set to false, observe here P1 is continuously checking this condition. Flag of 0 is true or not. Now the flag of 0 is not true. It is false. That means the false is equal to true is false only. So now this condition has become false. Observe here false and false. Now it has become false. Once it has become false, now P1 can come into the critical section. Understood. So this way, where it has been done, it has unlocked this one. This is called unlocked. Unlock is nothing but now whichever is locked by P naught has been unlocked in this exit section so that P1 can enter into the critical section. So we have achieved the mutual exclusion, which when one process enters into the critical section, another process cannot enter into the critical section. Third one, you see, our third requirement, which is called as bounded wait. Always, we are not giving chance to the only one process to enter into the critical section. If once P naught is done, we are giving chance to P1. If it wants to enter into the critical section where the requirement is given true, if it is false, if again P1 wants to enter into, if again P0 wants to enter into the critical section, only it can be given a chance. But if both are competing, then always only one process cannot be given a chance. One after the other, the chance is given, which is called as bounded wait. I hope you all are clear. The second requirement is progress here. Progress is nothing but if P0 and P1 initially both they don't want to enter into the critical section. If both want to enter into the critical section, then depending upon the statement the CPU has been adopted. Quickly, the decision between P0 and P1, whom to give the execution first or whom to give in the chance to use the critical section has been decided very quickly depending upon the CPU time. Right. I hope you all are clear. All these three requirements are very much satisfied by using this solution, which is named as Peterson solution. Right. So this process is working very much better for two processes only, P0 and P1. I hope you all are clear with this Peterson solution, which is your software solution. Right. But if you have more than one process, here we have considered only two examples of P0 and P1. But if you have more than one process like P0, P1, P2, P3 like that, then Peterson solution cannot be used. For that, we have our another solution, which is our hardware solution. In our next lecture, we will understand about the hardware solution to the critical section problem. Let us all meet in the next lecture. Until then, thank you all of you.